All right, we are live. What's up, everyone? Thank you all for coming out today. This is week 4 of the reverse engineering group. Today we're going to be talking about the stack a bit more in depth, covering the stuff it's going to do, what it does, why it exists, basically the ramifications of it, and then some more in-depth material. So, to cover the material we covered before, the stack goes downwards. So the stack initially starts off at a high memory address, so like numerically high. And as you add more items to the stack, it's going to go downwards. So this means that subtraction makes the stack bigger and addition makes it smaller, so it's kind of the inverse of what's logical, but it's what the memory space is allocated for. Items that are known at compile time are stored on this because this is used as sort of like a semi-dynamic growth place, but it's supposed to be known at compile time how large it is. And it's a LIFO queue, so if you push stuff onto it, it's going to come off in the reverse order that was put on there because it's like stacking plates atop each other. If you put a bunch of plates on top of them, you can't get the first one without pulling the rest off first, otherwise you're going to break a lot of things. So this leads to local address spaces, which leads to function scoping. So C uses stack frames in order to create or to preserve local scope. So this is where your local variables are going to go. Global variables are stored elsewhere. This is where anything defined inside of your function is going to be saved. So that way when you call another function, it's able to be retrieved. Setting up the stack is what's known as the prologue. This is the code that happens at the start of every function in order to declare and allocate the stack space. When you tear it down, that's called the epilogue. That is when the stack is restored, and then you basically jump back to the function you called previously. So with that, here's a sort of overview I drafted up on how the stack looks in its relation to RBP and RSP. So basically you have like the previous stack frame contents in red there, and then this is like right after it's been called and the stack has been set up. You basically have the return address, which is put there by the call instruction. We'll get to that. The pointer to the previous frame, which is RBP, so sorry, that's going to be RSP. And then that's going to get decremented down to where it shows on there. And then you have that space for all your variables. This is to show like how all those local variables and data points are going to get referenced. Note that the return address is not part of that. That is because that is handled by the call and ret instructions basically exclusively. You're almost never going to be popping and manipulating that directly until we get to buffer overflows and stuff. Wink, wink, nudge, nudge. So calling, when you're calling a function, you have to perform operations on the stack to prepare it. So you have to basically set up the environment for a new frame to be created. When you create a new frame, you need to save the location you want to come back to. So when you inevitably jump to this new frame's data location, pretty much, basically the code where that frame is going to be used, you're going to need to jump back to that address at some point. So in order to preserve that, you need to put that address on the stack. That's what the call instruction does. So that's going to move RIP, which is the register that contains the address of the next instruction to execute. It's going to put that on the stack, and then it's going to execute a non-conditional jump to the address provided afterwards. So this is just saving the return address and then going to a new location. This way, that when you want to return back to your old location, you simply retrieve that address and then you jump to it. So once you've jumped to this new location, you have to build a frame. So you have multiple ways to do this. The two common ways are enter and the manual way, which is setting it up with saving the RBP, moving the RSP, and yeah. So we'll cover that too in a later slide. Enter does this automatically. It's basically a directive that you provide it a size. So you'll say enter 16, and that will set up a stack frame of 16 bytes. There's also another there's like another iterative argument, which is like 0, 1, 2, 3, 4, so that'll set up 0, 1, 2, 3, or 4 instances of that stack frame. However, a lot of times you're just going to leave that at 0 because, or 1 maybe? I can't remember which one's the default to do it, but so enter will basically generate a stack frame for you without having to actually remember the manual prologue of, yeah, I don't even remember it honestly, I always use these. So, the inverse of this is the leave instruction. So what the leave instruction is going to do is it's going to basically destroy the stack frame. It's basically going to move the stack pointer back to the base pointer, and then it's going to pop the data off the stack into the base pointer because that's where the old base pointer was saved. So it's basically just going to take the stack, slide it backwards, and then slide it back to the old frame in a two-part step. And then typically after that, you're going to call ret, because if you're calling this, you're pretty much returning from a function. So you want to destroy the stack frame and then return. So you'll typically see a ret instruction followed, which also operates on the stack, as I mentioned earlier. So returning, you basically want to restore the old base pointer, which is what leave does. You restore the stack pointer if applicable. That's what leave should also do. And then you restore the return address and jump to it. And that's what the ret instruction does. It basically pops the return address out of the stack because that was saved by the call instruction, if you remember. And then it'll basically execute a non-conditional jump to that. So as you can see here, there's an equivalent right there. That's not actually what it executes, but that's basically, for all intents and purposes, of a distilled version of what it does. So you can kind of see it in simplified assembly instructions. So does everyone understand how a stack frame is created, managed, and destroyed? Is there any ambiguity? Has anyone lost a bit? Real good? All right. So with that, we're going to go to a frameless stack, which is just a little bit of a twist on a regular stack. This isn't really super common. It's not like super different. It's not like going to change your world or anything. It's just like a little optimization that that some compilers will apply to a stack if they notice a certain set of conditions are met. What this is it's basically a stack where the RBP and the RSP are the same. So basically the stack frame is set at 0 bytes. Why does it do this? It does this because if the function that is currently entered does not call any other functions, you have no need to build a stack frame because you are the top of the stack. You know you're the top of the stack, and you know that there's nothing going to be put on top of you since there's nothing being called, nothing being jumped to, or anything like that. So what these will do is they will just set the RBP to the RSP, and that'll basically put them at the top of the old frame, and then it'll just play with the memory past that however it wants without actually structurally defining it. Not every compiler does this, and it's not like a super big deal. Like you'll still see everything that's going on. It just changes a bit how the prologue and epilogue look. I've got a slide in the next thing that'll tell you that. There's also a Godbold GCC generated entry I made showing framed versus frameless. So there is a framed function and a frameless function where I wrote them such that they would be compiled framed and frameless. So this is just some basic, really quick overview of how it looks. You'll notice that basically the subtraction for the bytes is not there, and the leave is replaced by a pop RBP because that's just restoring the old RBP since the stack is pointing to that currently and there's nothing really on top of it that's been pushed. If you look at the framed and frameless, this is basically what they do. It's, like I said, it's not super different. It doesn't change the body of the function at all. It just changes how it looks at the prologue and epilogue. Is anyone confused by that? That's actually something I learned like just the other day when I was looking at some disassembly, so it's not like it's incredibly common or useful. But I figured it's just good to put on there so you guys know if you come across that and see something a little bit different than what you're expecting.
So you've never seen it?
Yeah, I had only seen that like the other day. I was putting together some code for the group and I noticed that I was like, oh hey, the prologue looks kind of weird. I started looking into it. It's just like a really simple optimization that's applied, so it doesn't need basically this instruction, and it saves like 1 or 2 cycles on the leave. So I guess it would, I don't know. It's not super. It's not like it's not going to increase your code speed by 1,000 times, but it's just a small optimization that the compiler makes. Yeah, so you'll just see it, the instructions are a bit simpler. But so this is only applied when you don't have a function call, because if you have a function call, you're going to have to create an entire stack frame. So that's when the frame comes in. So the side effects of the stack. So there's finite space for the stack. You can't just infinitely grow your stack. There's only so much memory allocated towards it. It's going to grow towards the heap as this little instructional drawing here shows you. They kind of grow towards each other. So what this means is that if you're using a ton of stack space for something, you're going to run out at some point if you're mismanaging or misusing it. If you define a ton of stack space at compile time that your program is not capable of handling, GCC will throw a compile error saying that there's like a stack out of bounds exception or something. it will say like, I cannot compile this, you are using way too much stack space. I actually had this happen when I was trying to find some idiotically large array or something that was just statically built. So I ended up having to change that a little bit. One thing this also means is that if you remember, as I said with framed functions, they're going to keep building a stack frame. So if you have a recursive function and it keeps recursing, it's going to keep building stack frames for itself. So what this means is eventually that's going to run out of stack space. So you only have so much depth of recursion that you can reach with C like this. And Java too, if any of you have written recursive programs in Java and you've gotten that like stack out of bounds exception or something, I believe it is, this is what's happening here is the JVM ran out of stack space and just threw its hands up and is like, well, crap, I don't know what to do now. Because the stack grew way too far, way too quickly, and it just kind of ran out of space and it had to abort through a processor exception. So what that takes me to is I'm going to have some assignment. Yeah?
When the OS sets up the program in memory, how does it know how big to make the space between the stack and heap? I know they're virtualized, but...
I cannot remember if that's defined in the program header or if it's just built by the operating system at runtime. I think that might be specified in the program header. I'm pretty sure it'll say like, hey, I need stack space for this big and heap space this big. But like since the stack is kind of dynamic, it doesn't know for sure like how big it is. Like if you have the infinitely recursive function, it won't know how many times it's going to recurse. It'll just know how big to build each frame. It doesn't know how many frames it's going to need. So it'll probably have, I think it has a header that'll say like, hey, I need this much space in this memory location. Anyways, so what that brings me to is this week, wow, I went really fast for this, sorry guys. I put together like a little weekend challenge sort of thing. So you're going to need to do some assembly for it. So I've got these resources here. GNU Assembler, GAS. It's the standard GNU tools assembler. It's what GCC uses and all those tools. It's very powerful. It's easy to use. It's got a lot of documentation. People have talked about it a lot. It's assembly, so it allows you to have complete control over the memory, address space, what's in the program, what it's doing, what it's executing. The only con is it's assembly, so you have to do everything on your own. You'll have to build the stack pointers and frames and manage calls and all that stuff. So I have an intro to GAS for like the syntax, writing executables in it, compiling stuff. And then for people who are really interested in it, I've got a deeper dive right there which goes much more in depth into topics and stuff that I think would be useful to be covered if this is something that really interests you. On the flip side of that, we have GCC extended assembly. GCC used to have a basic assembly directive. It's like __ASM __, and you can basically inline assembly directly into your C code. However, that did not allow for much extensibility and usability. So what they did is they wrote the extended assembly function, which will allow you to inline assembly into your code, but it will also allow you to input data into the registers and output data from the registers into variables. So this is very easy if you're writing assembly snippets that don't need to manage the entire program address space. If you just want to like test something out, you can like make an integer and then you can pass the integer into some assembly snippet that screws around with the integer. You can pass it out and then printf it. So this is awesome because it allows you really easy access to the C standard library functions while also giving you access to assembly code. So it's great for just running simple snippets, screwing around. I've got a link here which will tell you basically the syntax of it, how to use it. It'll tell you what the assembly syntax is, it'll tell you what the function is and what inputs and outputs it expects. So like one of the arguments to the function is the assembly, one is input registers, one's output variables, and then there's like a clobber one, I believe, where it asks for the registers that are going to get overwritten. Anyways, why I have this on here, and these are some resources I have for what we talked about. If you can't tell, I really like this site. Basically, it contains a listing and explanation of a ton of assembly instructions, how they're used and what they do. Definitely read up on that if you find an instruction you don't know. It's awesome. Anyways, why I'm talking about assembly. I'm making optional weekend exercises. So in one of those resources, specifically this one, which explains how binary files, memory layouts are read and looked at, he says he thinks it would be great if there was an easy way to read the process memory map. Grant his wish. So this exercise is basically write a script that is able to read that file and present the memory maps in a very readable, easy to understand way. You can make it script friendly, so that it's able to be passed into a script. You can make it output into a table. You can do whatever you want. This is just kind of something to focus you guys and try to get you interested in. Yeah, so it should just be a simple script that'll input data from that file and output data to standard out, whatever you want. Make it however you want. I'm not here to tell you how to do it. For those of you who want to get a bit more hardcore into C and assembly with this sort of thing, I have exercise 2, which is going to build heavily on the top of the stack frame recursion method I was talking about, where if you build too many stack frames, your program is going to crash. What I want is I want you to build I want you to build a function that can calculate Fibonacci sequences recursively without crashing for any large number given. This is possible. This is known. This is a known problem. It's definitely possible. It will require a bit of fuckery with assembly for sure, because C by default will not generate these. Actually, as a little hint, or not hint, or direction or something, the standard GCC flags should not generate an executable that is able to compute this. GCC compiled with -03 will be able to complete this. If you look at the differences between that, you can sort of figure out the optimizations it's applying. Sorry, I'm getting ahead of myself. There's a specific way you have to write this in order to get that to work like that. And then if you want to go even farther with making O3 able to compute this, you can actually write some assembly directives directly into the C code with the inline extended assembly I was talking about. You can write some assembly right into the C code, and I want to see if you can make it do that without the optimization. This is just kind of as like a weekend exercise. You guys should have no obligation to do this. I will talk about the answers to the ones that I do or have the time to do next time we meet. But I think it would be a really good exercise for you guys to figure out how the stack works, how all this stuff is put together. It'll give you a really solid understanding for when we talk about buffer overflows and printf vulnerabilities in the future. Like I have on here, if you get stuck, just shoot me a message or something, email me. I will help to the best of my ability. Tell me if you want guidance or if you want me to just like outright say something that you're stuck on or whatever. I really want you to see you guys like do well at this. I'm not writing these to be hard. I'm writing these because I see them as a good way to understand a topic very in depth. If this is proving a little hard, work on the memory map layout one. That will also prove very useful for when we talk about memory mapping and how that relates to buffer overflows and stuff. However, this will be a bit harder, but in my opinion is a bit more rewarding. I've partially solved it. Unfortunately, I haven't actually written a solution to it yet because I've had classes, but I'm also going to work on it this weekend. So I think that these will be fun. If you guys enjoy it, don't enjoy it, please give me feedback. I'm trying something new with this. Yeah, I think that is about it. Thank you all. I'm sorry that this was so short. It's hard to prepare these slide decks and examples with classes and work and stuff, but did anyone not understand something I was talking about or have a question about the exercise, something I mentioned, whatever? Yeah?
Yeah, so for the second exercise that we're supposed to write in assembly, like you said you didn't want us to use registers for that?
Yeah, so the point of this is to solve the problem of stacked frames and their growing and shrinking. So if you don't use a stacked frame, basically it just gets rid of the entire point of the exercise, because I trivially wrote an x86 program that was able to solve this because it's basically iterative at that point. You're just iterating back and forth and stuff. It's
What if I keep the scope with the...
well, so that's what I'm saying, is you need to build a stack frame. You need to, if you don't, just use enter and leave. Like, make a function that uses enter and leave, call and ret, and see if you can finagle it a bit enough to get, so maybe not call and ret. So call and ret should not be required. It will be helpful to set up an assembly program that works. It will not be helpful to set up one that will work for this specific problem, so you'll need to like modify it a bit. It's a bit esoteric. I'm sorry if I'm not explaining it well enough, but basically for the x86 program, you should definitely be building a stack frame and storing the integers in that. Otherwise, you're basically sidestepping the whole reason I'm proposing this, because it's very easy to write an assembly program that will just solve this without any stack frame. Yeah. So you are more than welcome to do that, but the point of this specific exercise is to get a very, very deep understanding of how the stack frame is working in relation to these calls and how to solve around that. So it's kind of like, it's like a mix of like assembly and mathematical acumen. It's not, you don't need a ton of math for this, but you definitely need to be comfortable with the Fibonacci sequence in order to work with this. Does anyone else have any questions about this? Awesome. Thank you guys for coming. Sorry that these are so short, but okay, go ahead, I guess, or whatever. Yeah, sorry these are so short. I just try and put more content in them than make them very long. But I'm definitely going to be trying to get more of these exercises out. I feel like these are a great way to learn topics in depth. I'll be doing my best to provide like a spread of them each week, like at least 2. That might not always be possible, and the challenges might not always be possible. I just kind of propose them as something you can work on to get a deeper understanding into it. If any of you guys have any problems with it or run into roadblocks or whatever, please talk to me. I'm just kind of throwing these out there. Let me know if you guys like them, don't like them. I don't know how to make this better if I don't get feedback. And definitely work with each other too, like ask questions in the channel, like don't just shoot me messages, say like, oh, hey channel, are you guys working on this? Are you able to get around this? Or I'm having this problem with this assembly or whatever. You look like you're, oh, okay. Awesome, I'm glad you guys came to this. I'm really happy to see how big it is and how much attention it's getting. That's pretty awesome. I wasn't really expecting this many people when I proposed the idea, so this is really awesome to see. I'd really like to get some people making presentations in the next few weeks. I know Jack has one coming up. He's going to be working on that with me. If anyone else wants to talk about something, if you guys want something explained to you, let me know. I'd be more than happy to fit it in somewhere. And with that, I think I'm going to call this to a close. Thank you guys. Yay. Also, someone please direct me, or someone please help me make a good theme for the site. I'm trying to get a site together for you guys, and I am the worst web dev you will ever see.